Hey everybody, this is a video for lesson 4.7, applications of logarithmic functions. 4.6, we talked about applications of exponential functions. So we're just going to look at a few applications of what logarithms can help with. And again, like all the other videos, take time to pause, write stuff down. Um, Anything that you feel like needs to be written down, make sure you pause the video and write it down. The main point of today's lesson is talking about what are called logarithmic scales. Logarithmic scales measure large spans of numbers. For example, we're going to look at the Richter scale, pH scale, and measuring sound. Those are all what are called logarithmic scales. You can see here I've got a fairly large span of numbers from 1 to 10 million. That's a very, very large span of numbers. And this could be anything from any kind of measurement. Scientists oftentimes don't like dealing with large spans of numbers or big numbers either. Um, Calculations can be cumbersome with large numbers or very, very small decimals. So oftentimes scientists will use logarithmic scales to make this span of numbers more manageable. For example, log of 1 is equal to 0. Log 10 is equal to 1. Log 100 is equal to 2. This is equal to 3. This is equal to 4, and so on and so on. So by using a logarithmic scale to measure this span of numbers here, we can narrow it down into a span of numbers from 0 to 7 or 0 to 8. And that's essentially what a Richter scale or a pH scale or sound measurement, which is in decibels, measures. So we'll start with the pH scale. So this is the formula you're going to want to write down for the pH scale. And that H plus is a measurement of hydrogen ion concentration in moles per liter. And the concentration of hydrogen ions in a substance, what I've written here, it's a very large span of very small numbers. By very small numbers, I mean very small decimals. And it's a very large span of very small decimals. For example, 3.16 times 10 to the negative 8. That's 7 zeros. Like that. Or 4.1 times 10 to the negative 4. That's So those are both small numbers, but it's a very large span between those small numbers. And these are actual measurements of hydrogen ion concentrations in different substances. This is a measurement of a sample of human blood, for example. So rather than measuring hydrogen ions concentration in these substances, the pH scale was developed to measure the acidity of liquids using logarithms. And it takes a span of numbers like these two numbers into a span between 0 and 14, 7 being neutral. Numbers less than 7 on the pH scale are acidic, and numbers greater than 7 on the pH scale are basic or alkaline. So an example here, Mountain Dew has a hydrogen ion concentration of 7.9 times 10 to the negative 4. Pepsi is 3.47 times 10 to the negative 3. Let's find the pH of both of those. So for Mountain Dew, pH is negative log 7.9 times 10 to the negative 4. For Pepsi, it's negative log of 3.47 times 10 to the negative third. So continuing this on, really at this point, it's just a calculator problem to finish this off. So we need to get the calculator, 7.9 times 10 to the negative 4. And negative log 7.9 times 10 to the negative 4. That's 3.1 approximately. And then for Pepsi, that's going to be 3.47 times 10 to the negative 3. So negative log 3.47 times 10 to the negative 3. That's 2.46. So this question here, which is more acidic? Pepsi is lower on the pH scale, which means it's more acidic. So those are examples of a pH scale or a logarithmic scale to measure the acidity of liquids. Another logarithmic scale called the Richter Scale, I'm sure you've heard of it, developed by a scientist, last name Richter, that's why it's called the Richter Scale, back in the 1930s. It measures the energy output of an earthquake by looking at what's called the intensity. That's what these two numbers here are, intensity. So I is the intensity of a quake measured on a seismograph. And I'm sure you've seen pictures of a seismograph. It's got that roll of paper with the needle that goes up and down. The intensity is what's called the amplitude of that graph, that wavy line. So the amplitude is this measurement here from the midline to the top. So that intensity is measured in centimeters. And then S is the intensity of what's called a standard quake. A standard quake is a quake that's just barely strong enough to register on a seismograph. Many quakes are so small in intensity that they don't even register on a seismograph. So as soon as a quake becomes intense enough to measure on the seismograph, that's called the standard quake, and its measurement here is 10 to the negative fourth of a centimeter. And then the magnitude is a logarithm of the ratio of the intensity of the measured quake divided by the intensity of the standard quake. So for example, if we have a magnitude, or we want to find the magnitude of an earthquake that has an intensity of 3.75 on a seismograph, so the magnitude is log of I divided by S, so 3.75 divided by 10 to the negative 4. And this just becomes another calculator problem. So this one would measure 4.57. On the Richter scale. A variation that you'll see on your homework is comparing intensities or magnitudes of two different quakes. So let's suppose we have an earthquake that measures 5.3 on the Richter scale, and then another earthquake that measures 7.1 magnitude, how much more powerful or how much more intense is that 7.1 magnitude? So we're comparing intensities, and we want to compare to see how much more intense. We need the intensity of the second quake divided by the intensity of the first quake. That's what we ultimately need to find to find out how much more intense. Was it twice as intense, 10 times as intense, 100 times as intense? In order to figure that out, we need a ratio. We need to divide the two intensities. So for the first quake, we have the magnitude, which is 5.3, and that's equal to the log. We don't know the intensity, so I'm going to call it I1, divided by S, which is 10 to the negative 4. And then for the second quake, we can say that the magnitude 7.1 is equal to log, and then it's intensity 2 divided by 10 to the negative 4. Remember that S, standard intensity of a standard quake, is 10 to the negative 4 centimeters. So now we just need to solve each of these equations for their intensity and then divide those intensities. So going back over here, to solve a logarithmic equation, we use a base on both sides, in this case base 10. So now we have 10 to the 5.3 equals I1 over 10 to the negative 4. We multiply both sides by 10 to the negative 4. The intensity of the first quake is equal to 10 to the negative 4 times 10 to the 5.3. And that's equal to 10 to the 1.3. When you're multiplying two terms that have the same base, you just add the exponents. So the intensity of the first quake is 10 to the 1.3 centimeters. For the second quake, do the same thing. I'm going to use a base 10 on both sides. So now I have 10 to the 7.1 equals the intensity of the second quake divided by 10 to the negative 4. If we multiply by 10 to the negative 4 on both sides, we have the intensity of the second quake is equal to 10 to the negative 4 times 10 to the 7.1. And then again, since we have matching bases here, we can simply add the exponents together. So the intensity of the second quake is 10 to the 3.1 centimeters. So now we're ready to figure out how much more intense by making a ratio. The intensity of the second one was 10 to the 3.1. The intensity of the first one was 10 to the 1.3. When we're dividing the terms that have the same base, we can subtract exponents. So 3.1 minus 1.3 is 1.8. So in terms of measuring or comparing the intensity, 10 to the 1.8, let's go back to our calculator. 10 to the 1.8 is 63 times as intense. 63 times as intense. What that means is a 7.1 magnitude is 63 times as powerful or more intense than a 5.3 magnitude earthquake. Quite a big difference there. Last one, measuring sound in decibels. So here's the decibel scale right here, which you're going to want to write down, and it acts very similar to the Richter scale. So I is the intensity of a sound measured in watts per square meter. And then I sub 0 right here is the intensity of a barely audible sound. Kind of like what we just talked about with a standard quake. I sub 0 is the intensity of a barely audible sound. And that intensity is 10 to the negative 12 watts per square meter. So just a quick example here, find the decibel level of a jet engine at takeoff if the intensity is 100 watts per square meter. So the decibel level is 10 times log of I divided by I sub 0. So the intensity of this one is 100. The intensity, if you remember, of the barely audible sound is 10 to the negative 12. And then this just becomes, again, another calculator problem. So 10 times the log of 100 divided by 10 to the negative 12, 140 decibels. Which is pretty dang loud, damaging to the human ear. You wouldn't want to be around a sound that loud without ear protection. So those are just some examples of how logarithmic scales can help scientific measurements